Well, you see, before we wander too far into the dark woods of spacetime, let me ask you something. Something simple, and yet, strangely unsettling. Have you ever wondered why the universe seems to guard the speed of light so fiercely? Like an old boundary stone placed at the very edge of reality itself. I mean, imagine it. Imagine a cosmos filled with stars drifting like lanterns on an endless sea. Drifting and drifting. Galaxies swirling in slow, majestic spirals. And threading through all of this, there is a rule, a limit, a line drawn in the fabric of existence, 299,792 kilometers per second. And, nature, mischievous, quiet, keeps whispering hints of exceptions. Quantum entanglement flickering like secret messages. Wormholes scribbled right there in Einstein's own equations. Even the expansion of the universe itself, stretching space faster than any beam of light could even begin to chase. So perhaps, just perhaps, you and I are standing at the edge of an ancient riddle tonight. If the universe really wrote a speed limit into its laws, why does the universe itself keep pointing to the cracks? And those cracks, could they be doors? Or are they not doors at all, but mirages, cosmic illusions shimmering out there in the dark? Before we go on, I'd like to ask you to subscribe to the channel and leave a like. My aim here is simple, to help you drift off to sleep while exploring the wonders of science. And, if you're still awake, just give me a little wave in the comments. Tell me where you're listening from, or what the night sky looks like above you right now. It's always fascinating to see who's joining us from all around the world. So let's continue. Well, you see, when we talk about light and its speed, we are really talking about something far more intimate than a number written in a textbook. It is the heartbeat of the universe itself, the rhythm against which every event, every movement, every story in the cosmos is measured. The speed of light is not just a speed, it is a boundary, a contour, a kind of shimmering shoreline in spacetime where our familiar intuitions begin to dissolve. And, that is the thing. We grow older, clocks tick, memories stretch and twist, and we often imagine time as something we drift through. But in physics, in the precise geometry that Einstein uncovered, time and space curl together in ways that make this limit, this cosmic speed, not a suggestion, but a structural truth. And, well, perhaps the most surprising part is that this limit is not enforced by any cosmic policeman. There is no rule book nailed to the walls of the universe. It is instead woven into the geometry of spacetime itself. And that, you know, is the beginning of the puzzle. Why should nature choose such a structure? Why should there be a maximum speed at all? And if that speed is so central, so defining, why do we keep discovering little hints, little suggestions at the edges of physics where the universe seems to whisper that perhaps the story is not quite finished? When Einstein wrote his equations, he was not merely proposing a new theory. He was suggesting a new way of seeing reality. Well, imagine you're moving through the universe, and as you push harder, as you accelerate, time begins to dilate. The seconds for you stretch, lengthen, slow. Someone watching you from afar would see your clock ticking ever more gently. And not just your clock, but anything that measures time. Your heartbeats, your thoughts, the rhythm of your breath. It almost feels poetic. Like time itself is resisting your desire to reach that cosmic boundary. And at the same moment, as your speed creeps closer to the speed of light, your energy needs begin to soar. Not just increase, but explode. To push an object with mass to the speed of light requires an infinite amount of energy. And, infinity here is not metaphor. It is an actual, unreachable wall in the mathematics of spacetime, and that is why the universe does not allow us to cross it. It is not a question of better engines or smarter engineering. It is not about building stronger rockets or using exotic fuel. It is the geometry itself. It is the way distances and durations warp as you move faster. So, imagine trying to reach that speed. You pump more energy into your ship, but each extra burst of power gives you less additional velocity than the previous one. It is as if space-time gently pulls back, saying not just no, but something subtler. Something like this is not the way. And you see, that is the heart of the problem. The cosmic speed limit is not an engineering challenge. It is a physical impossibility in our current understanding. It is built into the very relationship between energy and motion. But even as we say that, even as we repeat the mantra that nothing with mass can reach or exceed the speed of light, there is a part of us, a human part, that cannot help questioning it. Not because we doubt the mathematics, but because the universe itself sometimes seems to hint otherwise. Little cracks in our intuition, maybe, or perhaps vast cracks. Quantum entanglement, cosmic inflation, wormholes buried deep in the equations. The universe seems to present exceptions that are not quite exceptions, pathways that are not quite paths, and, well, that leads us back to the question that refuses to die. Why should such a fundamental limit exist? And is that limit as absolute as it seems? The special theory of relativity tells us that as one object approaches the speed of light, the time it experiences slows relative to an outside observer. If you travel fast enough, the stars themselves shift around you, the colors stretching and contracting, the sky reshaped by your motion. This is not science fiction. It is the real, measured, experimentally tested behavior of the universe. And yet, in that slowing of time lies one of the great paradoxes of human imagination. Because from your point of view, inside your speeding vessel, nothing seems out of the ordinary. You do not feel heavier. You do not feel time stretching. Everything is normal. The world outside is what warps. And that is where the beauty lies. Relativity does not just bend time. It bends the way we understand experience. Two people can disagree about the length of the same moment, the size of the same distance, the order of the same events, and both be correct. And, what could be stranger than that? Perhaps the speed of light is not a wall, but a reflection of how space-time behaves when we try to move through it. Perhaps it is telling us that motion is not as simple as pushing against the void. It is more like gliding across a structure that can ripple and fold. And in that structure, light is the fastest ripple possible. The material of space-time can carry disturbances only so quickly, and everything made of mass must dance to that rhythm. And so, when people imagine breaking the speed of light, they sometimes picture simply going faster, as if speed alone were the key. But it is not about speed in the traditional sense. It is about how motion interacts with space-time. The faster we move, the more space-time resists. It is like trying to swim across a river whose current grows stronger and stronger the more vigorously you try to cross it. Not just stronger, but exponentially so. A river that reshapes itself to forbid your crossing. And, well, there is also the question of causality. If something could move faster than light, it could outrun the very signals that define before and after. Cause and effect would blur. Events could occur out of order, You might receive a message before it was sent. And, whether the message even makes sense then, well, whether it exists at all. This is not just a philosophical worry. It is a mathematical certainty. The structure of spacetime would allow paradoxes to flourish if faster-than-light motion were easy, or even possible. But here is where things become wonderfully strange. Because even though relativity forbids objects with mass from crossing the speed of light, it also gives us glimpses of phenomena that seem to whisper about loopholes. Not loopholes that break the laws, but loopholes that reinterpret them. You see, the cosmos does not forbid faster-than-light expansion of space itself. It does not forbid entanglement correlations leaping from one side of the universe to the other in an instant. It does not forbid the geometry of spacetime from bending in such a way that two distant points lie next to each other. And that is where this journey truly begins. But before we move to those possibilities, we must sit with this limit a little longer, breathe with it, feel its weight. Because understanding why the speed of light is sacred is the first step toward understanding why nature sometimes seems to bend that sacred rule without breaking it. Think of it this way. Imagine time as a landscape, not just a sequence of moments. A landscape we travel through. And the speed of light defines the steepness of that landscape, the curves and slopes and boundaries. It is not merely a number, it is the shape of the journey itself. And, perhaps that is why Einstein's theory feels so profound. It tells us that when we talk about speed, we are really talking about the shape of reality. When we talk about limits, we are talking about the architecture of existence. And when we talk about the speed of light, we are talking about the deepest relationship between mass, energy, and the flow of time. So, even though it seems like a hard and absolute constraint, there remains the question that will guide us onward. If the speed of light is the structure of the universe, then what happens when the universe itself changes shape? What happens when space expands? Or when quantum states blur? Or when gravity twists the geometry? Not just bend it, but fold it. Well, you see, that is where things become even stranger. The universe may obey its rules with unwavering loyalty, but it also leaves clues that these rules are not the whole story. And, if there is more to the story, then where does the next chapter lead us? Perhaps into the quantum world, where distance loses meaning. Perhaps into the heart of entanglement, where connections transcend space. And with that, we step quietly toward the next mystery. The one that has confounded physicists for decades, a phenomenon that seems instantaneous, impossible, yet undeniably real. The delicate and bewildering world of quantum entanglement. And, as we step from the quiet edge of relativity into the strange interior of the quantum world, it feels as though the ground beneath our feet begins to shift. The certainties of spacetime, the clean geometry, the tidy cause and effect that comfort us, begin to flicker. It is as though we are entering a room where the lights never quite stop trembling. And, perhaps that is fitting. Because quantum physics does not simply challenge our intuitions, it dismantles them gently, then hands us something far more mysterious to hold. Well, you see, entanglement is one of those ideas that sounds like fiction until you realize that the universe insists upon it again and again through thousands of experiments. Two particles created together can become linked in such a profound way that what happens to one seems instantly echoed in the other, no matter how far apart they drift. And that is where the mind stumbles. because it is not just a matter of correlation, not just two coins flipping the same way by chance. It is deeper. It is structural. It is built into the wave function itself. When we say a change here is mirrored over there, we do not mean at some speed. We mean without speed at all. No travel, no message, just a single underlying state revealing itself from two places in space. And, if you pause to picture that, you might imagine a kind of cosmic whisper, but it is not whispering. It is not sending anything. And, that becomes the heart of the paradox. It is instantaneous without carrying information, connected without communicating. So, how do we live with that? How does it fit with the idea that nothing can outrun light? It seems impossible, but the impossibility lies only in our assumption that space is a container of separate things. Entanglement suggests that the separation might be an illusion born from limited perspective. The two particles are not two objects talking across distance. They are one state unfolding across distance. Imagine you have a book torn in half, and you send each half to opposite ends of the universe. The moment you read a sentence in one half, you know what must be in the other. The knowledge feels instantaneous, but it is not sent. It is simply revealed. But this metaphor, fails in one crucial way. The book already had the words written, fixed, predetermined. Quantum particles do not. Their properties are not decided until the moment we measure them. And that is when the true strangeness arrives. They are not revealing information that was hidden. They are revealing information that did not exist yet. And that is perhaps the reason so many physicists, from Einstein to Bell, found entanglement uncomfortable. Not because the mathematics is unclear, but because the implications are. If nature allows two distant events to be connected in this way, then what does distance even mean? What does locality mean? And why does the universe place such a strict limit on information, while simultaneously showing us correlations that ignore that limit entirely? Entanglement feels like a contradiction, but it is not. It is a quiet reminder that the rules of the quantum world operate beneath spacetime, not within it. And, that brings us to the next crucial point. Even though entangled particles seem to influence each other instantly, they cannot be used to send a message. You cannot encode a signal in a measurement outcome because the outcomes are random. Perfectly correlated, but random. And, that is where the no communication theorem steps in. This theorem tells us that entanglement cannot carry useful information faster than light. You can share correlations, but not choices. You cannot decide what the particle here will reveal. You cannot control the outcome there. The universe preserves causality carefully, as though guarding the unfolding of events with invisible hands. And, well, that is the difference between connection and communication. It is not just that they are not the same. It is that they cannot be the same without tearing the fabric of time apart. So entanglement gives us this extraordinary non-local link, but it never allows us to cheat the cosmic speed limit. It is not a tunnel. It is not a signal. It is more like the echo of a deeper unity. A unity so subtle we see it only when we look at the smallest scales. And, the more experiments we do, the more we find this unity confirmed. Photons, electrons, atoms, even molecules large enough to contain thousands of particles, all capable of being entangled. And each experiment whispers the same message. The separations we see are not as fundamental as we think. And that leads to an unsettling thought. If entanglement is real, and it is, then perhaps the classical world we inhabit is not the foundation of reality, but an emergent layer resting atop something stranger. So, when we say nothing travels faster than light, we might be speaking only about this emergent layer, the surface, the appearance, the skin of reality. Underneath, the connections might already exist. Well, you see, the universe at the quantum level does not care about distance. It does not treat here and there as fundamental. It treats them as labels, coordinates we impose on a deeper state. The entangled pair never split into two separate pieces. They remain one mathematical object, one wave function, even when placed on opposite sides of the universe. And, that means the question is not how they communicate. It is why we ever believed they were separate in the first place. But here is the problem. Even though this connection defies locality, it still refuses to let us send signals faster than light. It gives us non-locality, but in a strangely polite way, respecting the universe's preference for causal order. And, that is what makes entanglement so enigmatic. It shows us exactly where the boundary of knowledge sits. We can know correlations faster than light, but we cannot influence them. And, perhaps that is why entanglement feels like a doorway. Not a doorway we can walk through yet, but one we can see just slightly ajar. It promises a universe larger than the one Einstein described. A universe where the foundations of space itself might be woven from these correlations. And, it is tempting to think that somewhere within that deeper structure lies a hint of faster-than-light travel. Not the crude speed of rockets, but something more subtle, more geometric, more, well, quantum. Still, before we leap ahead, we need to sit with one of the strangest feelings entanglement evokes. The feeling that distance might not be a thing, that the world we experience is stitched together by relationships, not by coordinates. And, the particles do not ask permission to correlate across impossible spans. They simply are correlated. They simply exist as one. And that is the thought that keeps physicists awake at night. If entanglement is fundamental, then what is space? Imagine for a moment that space is not a stage, not a backdrop, but a consequence. That what we call location emerges from deeper quantum links. If that were true, then entanglement is not weird. It is the foundation. And locality, the idea that objects influence each other only through space, is what must be explained. And, well, if that is the case, then the no communication theorem becomes not just a rule, but a clue. It tells us that even though the universe is woven together beneath the surface, the layer we inhabit behaves with consistency, with order, with a kind of elegant restraint. It suggests that spacetime is a tapestry draped over a quantum web, and the speed of light is the tension in that tapestry, and entanglement shows us the threads underneath. So, when physicists say entanglement does not allow faster-than-light messages, they are not denying its profundity. They are acknowledging its complexity. The universe is telling us something delicate. The deep connections exist, but they do not break the world we live in. Well, that leaves us with the lingering question. If entanglement is real, and non-locality is real, then how do we reconcile it with the clean causal structure demanded by relativity? And the answer, or at least the beginning of one, arrived through one of the most beautiful ideas in physics. An idea proposed by a quiet, thoughtful physicist named John Bell. And, Bell did something extraordinary. He turned the philosophical debate between Einstein and Bohr into an equation, into something testable, measurable, falsifiable. And, those tests changed everything. So as we drift now from this shimmering quantum strangeness toward the next chapter, the one where Bell's theorem awaits us, we begin to sense that the universe is not asking us to choose between locality and quantum mechanics. It is inviting us to understand how both can be true in a reality more subtle than either theory alone can describe. And, when we step from entanglement toward the question of what it truly means for a universe to be local or non-local, we inevitably find ourselves standing beside the quiet figure of John Bell. Well, you see, Bell was not the sort of physicist who shouted his ideas. He wrote them almost gently, with the kind of clarity that feels, even now, strangely disarming. And that is fitting, because what he uncovered was something enormous. Something that forced us to confront the possibility that the universe is not stitched together in the way we once believed. Growing out of that long debate between Einstein and Bohr, the one filled with metaphors and paradoxes and deep philosophical discomfort, Bell asked a very simple question. What if we stop arguing and test it? And, the beauty of that simplicity is that it cuts through decades of speculation. Einstein insisted the universe must be local, that influences cannot travel faster than light, that reality must be, in some fundamental sense, complete before we look at it. Bohr resisted that view, suggesting instead that quantum mechanics does not need hidden variables at all, that the world is simply stranger than our classical intuitions allow. So, Bell took both views seriously. He wondered whether entanglement could be explained by information carried locally, by some hidden parameters assigned to each particle at the moment they were created. If such hidden variables existed, they would work quietly behind the scenes, ensuring that the measurement outcomes always matched the predictions of quantum mechanics. They would, restore the sense of locality Einstein hoped for. They would make the universe intuitive again. But Bell did something subtle. He showed that any local hidden variable theory must obey certain statistical constraints. These constraints, which later became known as Bell inequalities, reflect the idea that local realism imposes limits on how strongly two distant particles can correlate. And, this is where the universe reveals its true nature. Because when the experiments were finally done, the correlations turned out to violate those limits, not just slightly, but decisively, repeatedly, beautifully. Well, you see, this meant something astonishing. It meant that the universe cannot be both local and realistic in the classical sense. It meant that either properties do not exist before we measure them, or influences are not confined to the slow crawl of light across space. And, either way, the comfortable picture we once had of separateness collapses. And that is the moment when Einstein's worry became prophetic. He called entanglement spooky action at a distance, not because he believed in it, but because he thought the spookiness revealed the incompleteness of the theory. Yet Bell showed that the spookiness is real. The universe does contain correlations that no local explanation can account for. And, what is even more remarkable is that these correlations do not transmit usable information. They exist and do not allow us to exploit them. They hint at something beyond space-time, but do not let us touch it. But, well, the story does not end there, because for years after Bell published his theorem, physicists performed experiments that always seemed to leave little escape routes open, tiny cracks through which a local realist might crawl. These loopholes included detection inefficiencies, communication channels that might exist without us noticing, or the idea that the settings of our instruments might somehow be influenced by hidden factors. And, each loophole could allow someone to argue that the universe was still local after all. Then came the modern Bell experiments. These experiments closed the loopholes one by one with exquisite precision. They ensured that particles could not communicate with each other, that detectors captured enough data to remove bias, and that measurement settings were chosen randomly and independently. In some cases, the choices were even linked to distant starlight, so far removed from human influence that the freedom of choice became almost cosmic. And, each time the results came back the same. Bell's inequalities were violated. Nature itself seemed to stand there on the laboratory table, whispering that locality is not a fundamental truth. So, what does that mean? What are we left holding after all this? The simplest conclusion is that the universe is non-local. Not non-local in the sense of passing messages faster than light, but non-local in the sense that the world does not break cleanly into separate pieces. It is not that one particle influences another across a distance. It is that they are parts of a single structure, one state spread over space. And that is a profoundly unsettling idea if you were raised on classical physics. We want distance to mean something. We want here to be here, and there to be there. But in the quantum world, that boundary dissolves. The experiment does not simply reveal correlations. It reveals the connectivity beneath the surface of things. And, well, this is where Bell becomes not just a theorist, but a guide. He shows us that the familiar picture of the universe as a grid of points connected only by local interactions is incomplete. He shows us that the deep architecture of reality includes relationships that defy the spatial separation we see. And, perhaps the most astonishing thing is that these relationships are lawful, structured, predictable. They do not allow chaos. They do not allow paradoxes. They simply reveal that the world is more interconnected than our senses would ever allow us to believe. And that is the true legacy of Bell's theorem. It bridges thought and experiment, philosophy and physics, intuition and bewilderment. It forces us to accept that quantum non-locality is real, but controlled. Real, but constrained. Real, but not communicative. And, in that delicate balance lies the continued survival of causality. Well, you see, causality is the thread that keeps the universe coherent. If information could be sent faster than light, the order of events could reverse, and cause could follow effect. The world would unravel into contradictions. So even though quantum mechanics gives us non-local correlations, it wraps them in mathematics that carefully preserves the arrow of time. And, perhaps that is why entanglement and Bell's theorem feel almost like messages from some deeper layer of reality. They tell us that the structure beneath spacetime has no respect for distance, but spacetime itself still guards causality fiercely. So, is the universe non-local? Well, yes, in the sense that its hidden structure contains connections that are not limited by distance. But, it is still lawful, still beautifully ordered, still coherent. It is not chaos. It is a deeper kind of unity. And, we are left with a strangely poetic image. The universe behaves locally on the surface, the level where we walk and breathe and measure time with clocks. But underneath that surface lies a web of connections that spans galaxies instantly. Not communication, not influence, but connection. And that opens a new way of imagining space itself. If space is not fundamental, if it is instead an emergent property arising from patterns of entanglement, then Bell's theorem is not just a test of quantum mechanics, it is a window. A window through which we glimpse the possibility that the geometry of the universe is not built from distances, but from relationships. And, if that is true, then the speed of light may not be a limit at all in the deeper picture. It might be a property of the layer we exist within, a boundary of the surface, not of the foundation. Well, you see, when we start thinking this way, Bell's theorem stops being a mathematical constraint and becomes something closer to a map. A map pointing toward a reality in which the limits of relativity and the strangeness of quantum mechanics coexist because they arise from different aspects of the same underlying structure. And, once you begin to see that possibility, you cannot help but wonder whether the universe has left us hints about how space-time itself might be manipulated. But, that leads us away from Bell and toward something more speculative, something dreamed of by physicists who dare to imagine bending space-time to our will. If Bell's theorem tells us that the universe is non-local, then the next question is whether space-time itself can be shaped, stretched, compressed. Whether instead of moving through the universe might move around us. And, that idea brings us irresistibly toward one of the most extraordinary concepts ever written in the language of general relativity, a concept proposed by Miguel Alcubierre, a concept where faster-than-light travel is not achieved by motion, but by geometry. And, perhaps that is where our journey must go next, toward the strange possibility of warp drives, and the dream that the limits of light might not be the limits of imagination. And, once Bell's quiet revolution settles into our minds, once we accept that the universe is bound together by relationships that stretch beyond locality, we find ourselves drawn inevitably toward an even stranger possibility. Well, you see, if the universe allows non-local correlations at its foundations, then perhaps space-time itself is not the immovable backdrop we assumed. Perhaps space-time can be persuaded, coaxed, shaped. And that is where Miguel Alcubierre steps gently onto the stage. Imagine you are not trying to move through space faster than light. Imagine instead that you are asking space to do the moving for you. We often picture motion as something we initiate, with engines pushing us forward, burning fuel to fight against the vast emptiness. But Alcubierre proposed something more subtle. He wondered whether you could create a bubble in space-time, a region where space in front of you contracts and space behind you expands. And in that bubble, you would not move at all. You would sit still, suspended, while the universe glides around you. And that is the heart of the warp drive. It is not travel in the conventional sense. It is geometry. It is reshaping the fabric rather than racing across it. And, the amazing thing is that general relativity, Einstein's great theory of gravity, does not forbid this. The equations allow space-time itself to contract and expand. They do not place any speed limit on that contraction or expansion. So, the warp bubble could, in principle, move faster than light relative to distant observers, while you, inside it, never break the cosmic speed limit. Well, you see, it is like stepping onto a moving walkway at an airport. Your feet remain stationary, but the ground beneath you carries you forward. And the walkway can move as quickly as the engineers design it. In the warp drive, space-time itself becomes the walkway. You sit quietly in the center, while space carries you across impossible distances. But, here is where the poetry meets the physics. To make space contract in front of your ship, you need to pull it inward. To make it expand behind you, you must push it outward. And general relativity tells us that this requires something deeper than ordinary matter. It requires negative energy density. And, negative energy is not just energy that is small or lacking. It is a type of energy that curves space-time in the opposite direction of normal matter. It is, in a sense, the reverse of mass. And that is not something we know how to create in large quantities. But the idea itself remains profoundly beautiful. Not just beautiful, but daring. You are not battling the speed of light. You're dancing with the fabric of the universe. You're not breaking a rule. You're using the deeper rules that sit beneath the surface. And, well, there is something strangely humbling about that. The warp drive does not try to cheat physics. It listens to physics. It takes the mathematics of general relativity seriously enough to ask, if the universe stretches, if it bends, if it expands faster than light during cosmic inflation, then why can it not be persuaded to do so in a controlled, engineered way? Well, you see, when Alcubierre first proposed the idea in the early 1990s, many physicists reacted with a mixture of excitement and disbelief. The equations were elegant. They worked. But the cost seemed insurmountable. To create a warp bubble large enough to carry a spacecraft might require more negative energy than exists in the observable universe. And, that number, even though we do not write it here, is unimaginably large. It is so large that the idea felt unreachable. But physics rarely leaves an idea untouched. Over the years, refinements emerged. New space-time geometries were proposed. More efficient warp fields were studied. And, some models suggested the energy requirements could be drastically reduced. Not gone, but reduced. And that is important. Because in physics, even a slight reduction can transform the impossible into the merely impractical. Yet the challenge remains. To bend spacetime this way, we need negative energy. And negative energy, while not fictional, exists only in peculiar quantum circumstances, in delicate, fleeting amounts. The Casimir effect is one example. It shows that quantum fields can, under the right conditions, produce regions of negative energy density. But these regions are tiny, short-lived, and fragile. They are hints, not solutions. They show that nature allows negative energy, but not that we can accumulate it, store it, shape it. And, that is the central tension of the warp drive concept. It is allowed by the laws of physics, but only if we possess something the universe rarely yields. It is like discovering the blueprint for a magnificent cathedral carved into a mountainside, and realizing the stone needed to build it exists only as grains of dust. But then again, that is often how progress in physics begins. Not with certainty, but with glimpses. Not with machines, but with mathematics. And perhaps the deeper meaning of Alcubierre's work is that spacetime is not fixed. It is malleable. It can be sculpted. And if the universe can shape itself, as it did during inflation, then maybe one day we will understand how to shape it too. Think of what it would mean. You would not traverse the stars through brute force. You would not need colossal engines or unimaginable fuel. You would let the universe carry you. It is not just efficient. It is elegant. And, elegance is something nature often rewards. The deeper philosophical question, of course, is what it means to reshape spacetime at all. If space is a dynamic fabric, then perhaps our place within it is not as static as we imagine. Perhaps motion is not something that happens within space, but something that emerges from our interaction with it. And when you twist the fabric, you twist the meaning of motion itself. Well, you see, when you imagine riding inside a warp bubble, it becomes strangely peaceful. You do not feel acceleration. You do not feel strain. You sit in calm, undisturbed spacetime, like a leaf resting on the surface of a stream. The stream flows, and the leaf moves with it, carried without effort. And that image is perhaps the most poetic part of the entire idea. But the universe is not always gentle, and Alcubierre's drive contains hazards. The edges of the bubble, the walls where the space-time curvature is strongest, might accumulate high-energy particles. These particles could be released violently when the bubble stops. The geometry itself might distort signals. Communication with the outside world could be disrupted. And, perhaps most troubling of all, you cannot start or stop a warp bubble without propagating information faster than light, which means that creating one might require faster than light effects before you even begin. And that loops us back into the paradox. The warp drive promises faster than light travel without breaking relativity. Yet the act of creating the bubble may demand something that relativity forbids. It is not a contradiction so much as a reminder that our understanding of energy, quantum fields, and space-time is incomplete. But there is another way to view this, not as a barrier, but as an invitation. The warp drive sits at the intersection of gravity and quantum mechanics. To make it real, we would need a synthesis, a theory that unites the two great pillars of modern physics. And, perhaps the warp drive is not just a speculative machine. Perhaps it is a guide, pointing us toward the shape of a future theory. Well, you see, the universe has never been shy about bending space. During cosmic inflation, the expansion of space-time dwarfed the speed of light. And even today, galaxies in the distant universe recede from us faster than light because space itself stretches. These phenomena are not cheats. They are features of the cosmos. They show that faster-than-light behavior is natural for space-time, even if it remains forbidden for objects moving within space-time. So, Alcubierre's idea is not alien to the universe. It is a reflection of the universe's own behavior. And that draws us toward a deeper question. If space-time can expand faster than light on cosmic scales, then might it be possible, one day, to harness that same mechanism locally, not just to observe it, but to reproduce it, to tame it, to ride it? Perhaps the answer lies not in the equations alone, but in the quantum fabric that underlies them. If negative energy can be stabilized, if vacuum fluctuations can be engineered, if the quantum fields that generate space-time curvature can be shaped with precision, then the warp bubble might transition from mathematics to engineering. Well, you see, science progresses not by jumping from impossible to possible in one leap, but by tracing the boundaries of what is allowed. And Alcubierre showed us a boundary that is strangely open. It does not forbid. It challenges. It dares us to push deeper. And so, as we drift at the edge of this idea, we begin to sense a quiet symmetry. The warp drive is a celebration of general relativity's geometric power, but to make it real, we need quantum mechanics. We need negative energy. We need an understanding of the vacuum that goes far beyond what we know today. And, that leads us naturally to the next question. If the warp drive requires negative energy, then what exactly is negative energy? Where does it come from? How does it behave? And why does the universe allow it at all? Perhaps the next step on this journey is to explore how space can push against itself, how emptiness is never truly empty, and how quantum fields whisper possibilities into the fabric of the cosmos. And that takes us gently toward the strange, shimmering phenomenon known as negative energy. And, as we drift from the dreamlike geometry of the warp bubble into the strange physics that might power it, we find ourselves standing at the threshold of something even more delicate, something almost ghostly. Well, you see, the warp drive asked for negative energy. And now we must face the uncomfortable truth. Negative energy is not just exotic. It is elusive. It flickers into existence only in the faintest corners of quantum reality. And that is where our journey turns inward, into the empty space between particles, into the vacuum that is not truly empty at all. The idea of negative energy can feel unsettling precisely because it inverts everything we think we know about the universe. We grow older, clocks tick, and energy is supposed to be a measure of the stuff that fills the world, the heat of stars, the motion of planets, the buzzing of particles. But negative energy is not just the absence of energy. It is energy below the 0 point. It is space-time bending inward rather than outward. And, if ordinary energy is the weight of existence, then negative energy is the pull of absence. So, what does it mean for the vacuum to contain less than nothing? How can emptiness become even emptier? The answer comes from quantum fields, the invisible sea that permeates all of space. According to quantum theory, even the quietest vacuum is not truly still. It trembles with fluctuations, tiny pairs of particles that appear and vanish in moments so brief they bend the meaning of time. And, these fluctuations mean that space has a kind of restless texture, a background hum that is woven into the fabric of the cosmos itself. Well, you see, when you place two metal plates very close together, so close that only certain wavelengths of vacuum fluctuations can exist between them, something remarkable happens. The plates feel a force pushing them together. This is known as the Casimir effect, one of the most beautiful demonstrations that emptiness is not quiet. And, the pressure between the plates arises because the energy density inside is lower than the energy density outside. In other words, the space between the plates contains negative energy relative to the surrounding vacuum. And that is extraordinary. It means that nature does permit negative energy under the right conditions. It is not forbidden. It is not imaginary. It is small, fleeting, fragile, but real. And, that small window is enough to keep the dream of warp drives and wormholes alive. Because if the universe allows even a sliver of negative energy, then perhaps one day we might learn to cultivate it. But, well, the Casimir effect is subtle. The amount of negative energy it produces is tiny, far too tiny to bend space-time on the scale of a spacecraft. So, the challenge becomes one of scale. We need more of something that the universe only produces reluctantly. The warp drive demands enormous amounts of negative energy because space-time resists distortion. To carve a bubble through space, to pull the universe inward and push it outward, requires a kind of leverage that our technology cannot yet imagine. And, that is the paradox we now face. The mathematics says yes. Quantum field theory says maybe. Engineering says not yet. And, perhaps the most profound question is not whether negative energy exists, but whether we can ever control it without breaking the universe's delicate rules. You see, quantum fields are bound by inequalities. They cannot dip arbitrarily far into negative values, nor can they remain negative for long durations. It is as if the universe allows negative energy only in small, whispered moments, as though permitting it but guarding it. And that protective behavior may be essential. If negative energy were abundant and easily manipulated, the structure of spacetime could unravel. Wormholes could form spontaneously. Causality could fracture. And, time itself could lose the clean ordering that lets us speak of before and after. So the vacuum gives us glimpses, but not gifts. It reveals possibilities while concealing power. And perhaps, well, perhaps that is part of the beauty. The universe is not careless with its mechanisms. It reveals just enough to keep us wondering, but not enough to let us tear spacetime apart on a whim. Still, there is something fascinating about how negative energy arises. It is not a substance. It is a pattern, a change in the distribution of quantum fluctuations, a reshaping of the vacuum's probabilities. And, that means it is not tied to matter or mass in the usual sense. It is part of the geometry of fields, part of the dance between presence and absence. And if geometry is flexible, then so is negative energy. Well, you see, when we think of energy, we imagine fuel tanks, furnaces, reactors. But negative energy is more like an instruction, a configuration that spacetime responds to. And that opens the door to a different sort of question. What if we could manipulate the vacuum itself? Not just push matter around, but push on the fields that define emptiness. What if technology, centuries from now, learns to sculpt the vacuum with the same precision we sculpt photons today? Perhaps the warp drive of the distant future is not built from engines, but from fields. Not constructed in factories, but woven into the quantum background. And that is not entirely fantasy. We already manipulate vacuum states in laboratories. We create squeezed light, quantum states with lower uncertainty in one property and higher uncertainty in another. And although these are not negative energy in the classical sense, they hint at the malleability of the quantum vacuum. And, squeezed vacuum states can produce localized regions that behave like negative energy, even if briefly. These experiments do not bend space in any dramatic way, but they show that our control over the vacuum is growing, slowly, carefully, but unmistakably. So, perhaps the true difficulty of the warp drive is not the scale, but the subtlety. Not the quantity of negative energy, but its stability. To create a warp bubble, you would need negative energy arranged precisely along the walls, stabilizing the geometry, preventing collapse. The arrangement must persist long enough for travel, remain uniform enough to keep its shape, and respond dynamically as the bubble moves. Engineering such a thing from quantum fields is beyond anything we can currently imagine. And, well, yet the existence of negative energy remains a profound reassurance. It means the warp drive is not excluded by physics. It is only excluded by our ignorance. And there is something else hidden within this idea, something quietly profound. Negative energy suggests that spacetime does not merely respond to matter, it responds to the vacuum itself. The universe is sculpted not just by stars and planets, but by the quiet, trembling sea of quantum fluctuations. And, That means the vacuum is not a background. It is a participant, a co-author in the cosmic story. Well, you see, that brings us to a broader realization. If emptiness itself can curve space, then space is far more dynamic than Einstein imagined. It is not just shaped by mass, it is shaped by the quantum fields that saturate the cosmos. And that is a hint of something deeper, something that pulls the warp drive and the Casimir effect into a larger pattern. A pattern that might one day serve as the foundation of a unified theory. But before we rush toward that possibility, we must confront another question. If negative energy exists, even in these delicate forms, then what else might it allow us to build? And, that brings us naturally to wormholes. Because wormholes, like warp drives, require negative energy. Not just require it, but rely upon it to keep their throats open, to prevent them from collapsing under their own gravitational pull. So, negative energy is not merely a curiosity. It is the key that unlocks some of the most astonishing shapes spacetime can take. And maybe the universe is telling us that these shapes are not forbidden. They are simply difficult. They sit on the farthest edge of possibility, waiting for us to understand the vacuum deeply enough to reach out and mold it. Perhaps one day, centuries from now, humanity will look back at the Casimir effect the way we look at the spark that first lit a fire. A small effect, a fragile one, but also the beginning of mastery over something far greater. And, if we ever learn to shape negative energy on macroscopic scales, then the warp drive and the wormhole cease to be dreams. They become engineering challenges. Well, you see, that is what makes this part of the journey so intoxicating. Negative energy sits at the boundary between the known and the unknown, between quantum mechanics and general relativity, between the vacuum we think is empty and the vacuum that is alive with structure. And that just might be the boundary we must cross to travel faster than light. And now, having traced the fragile threads of negative energy through the quantum vacuum, there is only one place left to go next. Toward the idea that spacetime itself might offer shortcuts, that geometry might provide bridges where distance collapses. Toward the shimmering, almost mythic structure that has haunted theoretical physics for decades. The wormhole. And, when we follow the faint, trembling path of negative energy into the deeper architecture of spacetime, we soon arrive at one of the most haunting ideas ever written into the mathematical language of the cosmos. Well, you see, if the warp drive bends spacetime around us, wormholes do something even stranger. They fold the universe in such a way that two distant points become neighbors. And that feels like stepping into a place where distance itself forgets what it once was. The idea emerged from the equations of general relativity almost by accident. Einstein and Rosen, in their search for new geometric solutions, discovered a structure linking two regions of spacetime. It resembled a bridge, a tunnel, a throat. We now call it the Einstein-Rosen bridge. And, although their original version was not traversable, it hinted at something astonishing. The universe might allow shortcuts. So, what does it mean to take a shortcut through spacetime? We imagine space like a sheet of paper. Draw 2 points far apart. Now, fold the sheet, let the 2 points touch, and suddenly the distance collapses. Wormholes are the mathematical expression of that folding, not just in 2 dimensions, but woven through the full 4-dimensional texture of the universe. But, well, there is a problem. The Einstein-Rosen bridge collapses too quickly for anything to cross. It pinches shut the moment it forms. The geometry does not hold. And, to keep it open, just like the warp bubble, we need negative energy. We need something that pushes space apart rather than letting it fall inward. And that is where the bridge becomes a challenge not just for engineering, but for our understanding of reality itself. If you imagine standing at the mouth of a wormhole, you would see a shimmering tunnel, not made of matter, but of geometry. The walls would curve away, showing the strange glowing imprint of the other side. And the most remarkable thing is that you would not be falling through space. You would be sliding through geometry. You step forward, and the universe simply rearranges itself around you. And, well, when physicists first realized this, it felt like a kind of cosmic poetry. But then came the harder questions. If wormholes are possible mathematically, are they possible physically? Can the universe support them? And, if they exist, might they connect distant stars, distant galaxies, or perhaps even different moments in time? Well, you see, to keep a wormhole throat open, negative energy must thread its interior like scaffolding. It must counteract the gravitational pull trying to pinch the tunnel shut. And this negative energy must be stable, persistent, and strong. Not just a flicker like the Casimir effect, but a sustained phenomenon. And that remains one of the greatest unsolved questions in theoretical physics. Imagine a wormhole large enough to travel through. A tunnel, perhaps kilometers wide, stretching not through space, but through topology. It might connect your location to a distant star, or to a region billions of light years away. You enter, and before you can take a single breath, before your thoughts can even catch up, you are somewhere else. The exhilaration of that idea is almost overwhelming. And yet, the mathematics insists on one thing. Without negative energy, the wormhole collapses. And, there is something humbling in that. We are allowed to dream, but nature reminds us that dreams require structure. They require the deepest laws to cooperate. But the real mystery is not that wormholes collapse. It is that the equations permit them at all. That should give us pause, because general relativity is not a playful theory. It is rigid, geometric, demanding, and yet nested within its equations is the faint outline of a tunnel that could stitch together distant regions of the universe. And if you think about that carefully, you begin to sense something profound. The universe does not forbid shortcuts. It simply hides them behind conditions we do not yet know how to satisfy. Well, you see, one of the most fascinating consequences of wormholes is the possibility of time shifts. If one end of the wormhole experiences time differently from the other due to motion or gravity, then traveling through the wormhole could allow you to arrive before you left. And that introduces paradoxes, not just narrative paradoxes, but paradoxes embedded in the logic of causality. And, yet once again, negative energy acts as a gatekeeper. It supports wormholes, but only under conditions that might prevent paradoxes. It is as though the universe is willing to offer shortcuts, but refuses to let us tangle the threads of cause and effect. So, can wormholes exist naturally? Could they be formed in the heart of collapsing stars, or during the violent expansion of the early universe? Could they be lurking in the cosmic fabric even now, so small we have not seen them, or so rare we may never see them? The honest answer is that we do not know. And yet, Whenever we find ourselves near the boundary between known physics and speculative geometry, it is often helpful to remember something. The universe is vast. It holds patterns we have not yet imagined. It may contain structures so subtle that we mistake them for emptiness. And, well, some physicists have wondered whether microscopic wormholes might form from the quantum foam itself, constantly appearing and vanishing like bubbles in a boiling sea. These wormholes would be far too small for anything to pass through, but they might contribute to the deep architecture of spacetime. They might even play a role in entanglement. And that idea lies at the heart of something we will explore later when we reach the strange bridge between quantum mechanics and gravity. But for now, the question remains: could a traversable wormhole be engineered? Well, you see, engineering a wormhole would require controlling energy densities far beyond anything we can create. It would mean shaping not only space, but time. And, it would require a mastery of quantum fields that is many centuries beyond our current understanding. Yet the fact that the equations allow it, the fact that spacetime itself does not forbid it, keeps the idea alive. So, what would it feel like to step into a wormhole? Picture standing before a sphere that is darker than shadow, not because it absorbs light, but because light bends around it. You step forward, and your vision stretches, folds, compresses. The tunnel opens like a blossom, and the most remarkable part is that the journey might feel instantaneous, not fast, not slow, but outside the meaning of speed. And, perhaps that is what makes wormholes so alluring. They do not merely shorten distances. They rewrite the meaning of distance. They erase it. They dissolve the barrier between here and there, between near and far, between now and then. But the universe asks a price. If you want a wormhole, you must supply negative energy. And negative energy, as we have seen, is rare, delicate, and fleeting. And, the amount required is immense. Still, there is something quietly hopeful in the fact that the price is not impossible. It is impractical today, but not forbidden. There is no physical law that says wormholes cannot exist. Only practical constraints insisting that we are not yet ready. The deeper mystery is whether wormholes might exist naturally in regions we cannot see. Black holes are strange objects. Their centers hide singularities, places where our understanding of physics breaks down. And some theories suggest that under the right circumstances, the singularity could connect to another region of spacetime, not just collapse inward, but bridge outward. But, well, even if such wormholes exist inside black holes, they would not be traversable. Nothing that passes the event horizon returns. So these would be one-way tunnels, sealed from the outside by gravity itself. And, that leads us to the great unanswered question: can nature build a stable, traversable wormhole? And if not, can we? We do not have proof of either possibility. And yet the mathematics continues to whisper that the universe has room for shortcuts, that spacetime is more flexible than we thought. Well, you see, at this point, the boundary between physics and philosophy begins to blur. Wormholes challenge our understanding of reality itself. They remind us that space is not a container, but a dynamic field. That distance is not fixed. That the cosmos is a shape that can twist into forms we have barely begun to imagine. And that brings us closer to a realization we cannot ignore. If wormholes are possible, even in theory, then the universe offers mechanisms for faster-than-light travel that do not violate relativity. You are not moving through space faster than light. Space is simply shaped differently. This tension between possibility and practicality is what makes wormholes so hypnotic. They reveal a universe that is both welcoming and cautious, open to extraordinary structures, yet guarded by deep quantum laws. And, our challenge is to understand those laws well enough to know how far they will bend. So, before we move on, we must pause here, on the edge of the wormhole, gazing into its impossible geometry. The walls feel alive, curving inward, glowing with negative energy. On the other side, perhaps, is a distant star, or a different galaxy, or something even stranger. And, as we take one final look into that shimmering throat, there is a question growing quietly in the back of the mind. If the universe already expands faster than light on the largest scales, then perhaps wormholes are not the only geometric path to faster than light motion. Perhaps the next part of our journey lies not in tunnels, but in the stretching of the cosmos itself. The great expansion that carries galaxies apart faster than light, all while obeying the laws of physics with perfect grace. And that is where we must go next, toward the vast, silent motion of the universe itself. And, as we drift away from the narrow, shimmering throat of the wormhole, there is a moment, just a brief one, where the universe feels impossibly still. Well, you see, after thinking about tunnels through spacetime, the next idea arrives almost like a shock, because the universe already offers a phenomenon stranger, grander, and far more powerful than any wormhole we could ever construct. The cosmos itself is stretching. It has been stretching since the beginning. And, in the farthest reaches of that expansion, something extraordinary is happening. So, here is the quiet truth. The universe is full of galaxies racing away from us faster than light. Not because they are moving through space too quickly, but because space itself is expanding between us and them. And that subtle distinction changes everything. Imagine placing dots on a balloon. As you blow it up, each dot drifts away from the others, even though none of them are moving across the rubber. The balloon is the one doing the stretching. And in our universe, space does the same. Distant galaxies are carried along with the fabric of spacetime, like leaves drifting on a river whose current grows stronger with distance. Well, you see, when we talk about a galaxy receding faster than light, we are not talking about it breaking cosmic law. It is not outrunning a beam of light. It is being carried by the expanding universe itself, and expansion is not limited by the speed of light. The rules governing how objects move through space do not apply to the stretching of space. And, that is perhaps the strangest part. The speed of light is a speed limit inside the universe, not a speed limit for the universe. So, even now, in this very moment, there are galaxies so far away that their recession speed exceeds the speed of light. Their light will never reach us. They are beyond our cosmic horizon. The expansion between us grows faster than the photons can cross it. And in that subtle, beautiful, heartbreaking fact lies a doorway into thinking about faster than light motion in a new way. Because if the universe itself can outrun light, then maybe the key to faster than light travel is not speed at all. Maybe it is expansion. And, that idea, using the universe's own behavior as inspiration, is one of the great seeds behind concepts like the warp drive. Not pushing through space, but letting space push you. Well, you see, This cosmic expansion is not uniform everywhere. It becomes more dramatic over greater distances. Galaxies relatively close to us recede slowly. Those farther away recede faster. And beyond a certain distance, they recede faster than light. Not just faster, but exponentially faster, as though space itself has a kind of restless ambition. And, when astronomers first realized this, it felt like a kind of cosmic awakening. The universe is not static. It is not even simply expanding. It is expanding with a speed that increases the farther you look. That understanding forces us to reshape how we imagine distance. Space is not a stage. It is a living entity, a changing entity. And sometimes it stretches in ways that defy our intuitions. But here is the key point, the one that links us back to faster-than-light travel. If the universe can expand space faster than light, why can we not use the same mechanism locally? Why not harness expansion instead of fighting motion? Why not ride the stretching of space the way galaxies ride the cosmological tide? And, this idea becomes even more powerful when we consider that the cosmic expansion is accelerating. Dark energy, whatever it is, pushes on the universe with a gentle but persistent hand. It makes the expansion grow over time, not shrink. And this acceleration means that more and more galaxies drift beyond our reach, carried by the very fabric meant to connect us. Well, you see, in a strange way, the universe is doing faster-than-light motion, not just in the past, not just in exotic mathematical scenarios, but right now. And that raises a philosophical question. If nature can expand space faster than light, then perhaps faster-than-light travel is not unnatural. Perhaps it is simply unfamiliar. To appreciate how profound this is, imagine you are watching a distant galaxy. The light it sends now will never reach you. The space between you grows too quickly. It is like trying to swim against a current that strengthens with every meter. And, if the current outpaces even light, you remain forever isolated. So, does this violate relativity? No, because relativity governs motion through spacetime, not the stretching of spacetime itself. The universe respects its rules beautifully. No object outruns light locally. No particle zooms through space faster than photons. But globally, across immense distances, the geometry shifts. The map itself stretches, and the travelers on it appear to drift apart faster than any local motion allows. And, this distinction is crucial. It means that the laws are not rigid walls, but elegant frameworks. They tell us what is possible within spacetime, not what spacetime itself can do. Well, you see, once you internalize this, something begins to stir in the imagination. If expansion is the key, if geometry is the key, then maybe our path to the stars lies not in rocket engines, but in shaping space. Not pushing ourselves forward, but letting the universe carry us. And, that brings us to a subtle transition. We have been speaking about the expansion happening now, the gentle stretching that pulls galaxies apart. But in the deep past, something far more dramatic occurred. Something that did not just exceed the speed of light, but rendered it insignificant. So, before we can truly imagine using expansion for faster-than-light travel, we must look backward into the earliest moments of the cosmos, when the universe swelled faster than any imagination could follow. A time when distances stretched immensely in the blink of an eye. When the entire observable universe expanded from microscopic to cosmic scales in a fraction of a moment. And, that period, known as inflation, holds the most powerful example that space-time can outrun light. Not just outrun, but completely eclipse it. And that is where our journey must go next. Toward the explosive, silent bloom of the infant universe, where faster-than-light expansion was not a rare exception, but the rule. And, when we turn our gaze from the gentle, steady stretching of the cosmos to its earliest moments, the scale of transformation becomes almost impossible to hold in the mind. Well, you see, what we call cosmic inflation was not just expansion. It was expansion unchained, expansion unleashed, expansion so rapid that even the word speed becomes meaningless. And that is perhaps the most profound reminder that space-time does not always obey the intuitions we form from living at human scales. In those first fractions of a moment, the universe blossomed, not gradually, but explosively. Distances that were smaller than atoms ballooned to astronomical sizes. And, this happened so quickly that even light, the great cosmic yardstick, became irrelevant. So, if we want to understand faster-than-light expansion, we need not look to science fiction. We simply need to look backward, toward the echo of creation itself. Well, you see, the inflationary period lasted for only the tiniest sliver of time, but during that sliver, the universe expanded by an unimaginable factor. Regions that were once close enough to share information became separated by distances that no signal could traverse again. And, that sudden stretching solved puzzles that had haunted cosmology for decades. Why is the universe so uniform? Why does the cosmic microwave background look the same in all directions? Inflation smoothed everything out, stretched everything out, and left behind the seeds for the galaxies that would later form. And that tells us something quietly profound. Inflation did not break the laws of physics. It used the laws of physics. It exploited the geometry of space-time, letting space itself grow faster than light while keeping all local motions perfectly subliminal. It's not that the universe cheated. It's that the rules were always deeper than we imagined. Imagine watching the infant universe from the outside, if such a vantage point were possible. You would see space erupt outward, not just rapidly, but exponentially. Every tiny patch doubling and doubling again, like a heartbeat accelerating into a roar. And the astonishing part is that there is no object moving through space. It is space. It is geometry. It is the scaffolding of reality blooming outward. And, well, inflation offers a powerful hint about what the universe is capable of. If space-time can be driven to expand that quickly under certain conditions, then perhaps the key to controlling faster-than-light travel is not propulsion, but the physics that governed those early moments. Perhaps the mechanism behind inflation still lies hidden in the fabric of the vacuum. So, what caused inflation? We do not know for certain. Many models invoke a field, sometimes called the inflaton, that filled the early universe with a kind of vacuum energy. When this energy dominated, it pushed space outward at an accelerating rate. And when inflation ended, that energy decayed, flooding the universe with particles, radiation, structure. The universe we see now is, in a sense, the cooled ashes of that fiery expansion. This inflaton field, if it existed, would be a cousin of the dark energy that drives today's gentle acceleration. And, that connection is tantalizing, because it suggests that the universe has more than one way to stretch space, more than one way to outrun light, more than one way to challenge our assumptions about motion, distance, and causality. Well, you see, Inflation also reveals that the universe does not fear extremes. It is not shy about bending its own geometry. It does not hesitate to expand faster than any particle could ever move. And that should make us pause. If the universe has already performed the ultimate faster-than-light expansion, then the boundary between possible and impossible is not as sharp as we once believed. And, there is something else inflation gives us. Clues, imprints, patterns frozen into the cosmic microwave background. Tiny fluctuations stretch to cosmic scales, marking the universe with a memory of its own birth. These fluctuations tell us that inflation was not smooth, but slightly uneven. And those slight unevennesses, those delicate ripples, later grew into galaxies, stars, planets, and eventually into us. So, in a sense, inflation did not just shape the universe, it shaped us. It shaped every structure we see. It shaped the night sky. It shaped the very possibility of life. The astonishing thought is that faster-than-light expansion is not some theoretical curiosity. It is the reason we exist. And if that is true, then perhaps faster-than-light expansion is not rare. Perhaps it is fundamental, a natural part of the cosmic cycle. And if we could understand the inflaton field, if we could tap into whatever drove inflation, then maybe one day we could recreate, on a much smaller scale, the conditions that allowed spacetime to roar forward at impossible speeds. And, that is where imagination and physics meet in a strange, delicate space. Because creating local inflation would not be like building a ship. It would be like sculpting the vacuum. It would be like tuning the energy of spacetime itself. It might allow us to create bubbles of expanded space, regions where distances stretch while we sit inside, carried effortlessly. Well, you see, that idea edges very close to the warp drive, not breaking the speed of light, but sidestepping it, using geometry as the engine, using inflation as inspiration. But, inflation also reminds us that such forces are not gentle. They are not subtle. They reshape everything they touch. And perhaps that is why the universe performs its inflation only once, in its infancy, when nothing fragile yet existed. Still, we cannot ignore the possibility. Inflation teaches us that spacetime is flexible, that expansion is a tool the universe can wield. And if nature can wield it, perhaps one day we might as well. And, this brings us to something even more unsettling, something hinted at in the mathematics of wormholes and entanglement, that the relations we see in the quantum world might not simply sit atop spacetime, they might generate it. They might be the deeper structure from which space itself emerges. Well, you see, if spacetime is emergent, then the speed of light, inflation, expansion, they are not fundamental. They are properties of the surface, not the core. And that opens a doorway toward an idea both radical and strangely inevitable. Perhaps space itself is woven from the threads of entanglement. Perhaps inflation, expansion, wormholes, warp drives, all are shadows cast by a deeper layer of reality. A layer where the fabric of the universe is not made of distances, but of connections. And that, quiet thought leads us naturally toward the next great mystery. Toward the question of whether space is something the universe builds on the fly. Whether geometry is not the foundation, but the consequence. And so, our journey must continue into that realm, into the possibility that space is not fundamental, that it grows from patterns, that the quantum world, with all its strangeness, might be the true architect of the cosmos we move through. And, As we step gently out of the roaring brightness of inflation, there is this strange quiet, almost as if the universe itself is pausing. Well, you see, inflation shows us space-time bending and stretching at impossible speeds, but it also leaves us with a deeper question, one that sits beneath all the geometry, beneath all the expansion, the question of what space actually is, and that whisper leads us directly into the quantum world, where everything we thought was solid begins to shimmer. The idea sounds outrageous at first, that space might not be fundamental, that the distances we feel, the shapes we draw, the geometry Einstein wrote so beautifully, might not be the foundation, but the consequence. And, yet when you look closely at the quantum universe, something begins to emerge. Something that connects entanglement, wormholes, information, and spacetime into one astonishing picture. So, imagine two particles entangled. If you separate them, their shared state remains one. The connection persists, even if they are light years apart. And then, in 2013, a bold idea was proposed. ER equals EPR. Einstein-Rosen equals Einstein-Podolsky-Rosen. Wormholes equal entanglement. And, well, in that single equation, metaphorical or literal depending on whom you ask, lies a bridge between geometry and information. Well, you see, the suggestion is this, that every entangled pair is connected by a tiny wormhole. Not a traversable wormhole, not a shortcut you could crawl through, but a geometric thread woven into the fabric of spacetime. And if that is true, then spacetime itself may be a vast tapestry of entanglement. The structure of the universe would be built not from distances, but from relationships. And that is a profound shift. It means that space is not a thing, but an emergent phenomenon, like temperature emerging from atoms, like solidity emerging from molecules. It is not fundamental. It arises from the pattern of quantum connections beneath it. Imagine tearing space apart, pulling two regions farther and farther away. If entanglement weaves space together, then as you reduce the entanglement between two regions, the distance between them grows. And, if entanglement disappears entirely, the regions drift so far apart that space between them simply ceases to exist. And that idea is supported by calculations in quantum gravity, where the geometry can be reconstructed purely from entanglement data. So, the shape of spacetime might not be written in coordinates or rulers or grids. It might be written in correlations, probabilities, quantum states. The universe, in its deepest layer, might not know what distance means at all. Distance might be something that arises only when enough entanglement stitches the world together. And, this has an astonishing implication. If space is emergent, then the speed of light might also be emergent. The limit that binds our motion, the barrier that defines causality, the constant at the heart of relativity, might be a property of the surface, not the core. Well, you see, that does not mean the speed of light is fragile. It is not a rule we can easily bend. It is more like the freezing point of water, a consequence of deeper interactions. It's not that the speed of light is arbitrary. It's that it emerges from the structure of spacetime, and spacetime emerges from entanglement. And that means faster-than-light possibilities might not violate physics if they operate at a layer deeper than spacetime itself. Not just faster than light in space, but bypassing the need for space entirely. Think of this. Entanglement correlations appear instantly without traveling. They do not carry information. but they reveal a world where separation is not fundamental. So, what if space-time shortcuts, wormholes, warp fields, inflationary pockets are all reflections of the same underlying truth? That connections come first, geometry comes second. And, this brings us back to ER equals EPR. If wormholes and entanglement are two expressions of the same reality, then wormholes are not exotic. They are everywhere. Every entangled pair is a thread. Every quantum correlation is a stitch. And space-time is the quilt. Well, you see, there are powerful hints from holography too. In certain quantum theories, gravity emerges naturally when you structure entanglement in a particular way. Change the pattern of entanglement, and the geometry bends. Increase entanglement, and space grows. Decrease it, and space shrinks. And that is incredible, because it suggests we could, in principle, shape spacetime by controlling entanglement. Controlling entanglement at cosmic scales is far beyond us now, but so was controlling electricity once. So was generating coherent laser light. So was manipulating the vacuum itself. And, well, the idea that engineering one day might involve designing entangled states of enormous systems is no longer purely fantasy. So, let's imagine for a moment. If spacetime is built from entanglement, then a sufficiently advanced civilization could sculpt spacetime by sculpting its quantum underpinnings. They could change the density of entanglement to create curvature, tunnels, expansions. They could build bridges not by shaping matter, but by shaping information. And, that would mean faster than light travel might not rely on propulsion or pressure or negative energy, but on rearranging the very threads that weave reality. Well, you see, the extraordinary part is that this does not require breaking relativity. It bypasses it. If space dissolves at the quantum level, if distance loses meaning, then moving faster than light becomes a question of choosing a different set of connections. That possibility is far beyond our current physics. But the seeds are there, in entanglement entropy, in tensor networks, in the holographic principle, in the mathematics of quantum gravity. All of them suggest the same thing. Spacetime is not the starting point. It is the outcome. And once you accept that possibility, something beautiful happens. You begin to see the speed of light not as a universal law, but as a property of the layer of reality we occupy. Like the ripple speed on the surface of a pond. The surface has its limit, but beneath the surface, the water moves differently. And, perhaps the universe invites us to sink deeper, to understand the machinery beneath spacetime. Because if we ever learn how geometry emerges, we may learn how to reshape it. Not just bend spacetime, but rebuild it from the bottom up. So, as we stand on this precipice, with entanglement beneath us and geometry above us, there is one more set of phenomena we must confront. Strange behaviors that look like faster than light motion, but never break causality. Tachyons, tunneling, phase velocities. They tease us with the possibility of speed without substance, motion without information. And, they ask us to be careful in how we interpret what it means to go faster than light. And that is where our journey must turn next. Toward the shimmering edge cases of physics, those oddities that move faster than light but never carry a signal. Toward the borderlands where intuition fails, but where understanding grows. And, as we step from the shimmering idea that spacetime might be woven from entanglement, we find ourselves facing a different landscape altogether. Well, you see, Before we leap into grand unified theories or dream about sculpting geometry itself, there is one last region we must visit. A borderland where phenomena seem to outrun light and yet somehow never break a single rule. A place where speed becomes slippery, where motion does not behave like motion, where even time hesitates. And that is where faster-than-light illusions live. These are the strange exceptions physics allows. Not true shortcuts through space-time, not warp bubbles or tunnels, but effects that appear to leap ahead of light while carefully avoiding the pitfalls of causality. And, it's important to linger here, because they show us that nature plays with speed in ways far subtler than we often realize. So, let's begin with the tachyon, the hypothetical particle that, if it exists at all, well, whether it exists at all, is forever beyond the speed of light. The idea is simple on the surface. While ordinary matter can never reach the speed of light from below, tachyons can never slow down enough to reach it from above. They would always move faster, always outrun photons, always dance beyond the horizon of causality. But, the moment you write the equations, a problem appears. Faster-than-light motion in relativity can flip the order of cause and effect, a signal sent into the past, a universe that contradicts itself. And, the mathematics spirals into paradox. So tachyons remain ghosts in the equations, allowed by some versions of the theory, forbidden by others, and never observed. And that teaches us something delicate. Faster-than-light behavior is not just about velocity. It is about information. It is about the arrow of time. And anything that lets information travel backward threatens the integrity of the universe. The cosmos defends causality with great care. But not all faster-than-light phenomena threaten causality. Some of them slip past it elegantly. Quantum tunneling, for example, is one of the most beautiful illusions in physics. A particle approaches a barrier it does not have enough energy to cross, and yet a moment later it appears on the other side. Not because it climbed over, not because it broke through, but because its wave function seeped through, like mist through a tiny crack. And, here is the strange part. The tunneling time, the time associated with this process, can appear shorter than the time it would take light to cross the barrier. It almost seems instantaneous, faster than light. But no information travels that way. The particle does not send a message faster than light. The tunneling event is probabilistic, not controlled. And so, causality remains untouched. Well, you see, tunneling reminds us that the quantum world does not measure time the way we do. It does not move step by step. It flickers, it jumps, it reshapes itself. And sometimes the appearance of speed is simply the appearance of probability finding a path. And then there is the phase velocity of waves. Imagine a wave rippling through a medium. The crest of the wave can travel faster than light. The mathematics allows it. And, nothing breaks, because the crest carries no information. It is not a signal, it is a pattern. And patterns can move faster than light without violating anything at all. The trick is that physics distinguishes between different kinds of motion. Group velocity carries energy. Signal velocity carries information. Phase velocity carries neither. So, it can outrun light without ever becoming something we can use. And that is the thread that ties these strange phenomena together. They tease us with faster-than-light motion and then gently remind us that nature guards information very carefully. Perhaps this is why so many faster-than-light dreams remain dreams. Warp drives require negative energy we cannot yet produce. Wormholes demand stability we cannot yet engineer. Tachyons threaten causality. Tunneling cannot carry messages. Phase waves cannot carry energy. And, somewhere in that mixture, we begin to sense the universe's boundaries. Not walls, but contours. Not prohibitions, but shapes. Well, you see, when we gather all these edge cases, the ghostly tachyon, the slippery tunneling event, the crest that outruns light but carries nothing, we begin to see that faster-than-light behavior is not simple. It's not about running faster. It's about structure. It's about the deeper organization of spacetime, the ways information flows, the ways probability behaves. And that reinforces something we felt earlier. If faster-than-light travel is ever possible, it will not come from pushing against the limit. It will come from stepping outside the layer of reality where that limit applies. Not just going faster than light, but moving differently. Using geometry, connections, entanglement, or fields that lie deeper than spacetime itself. Perhaps that is why these strange, faster-than-light, but not really phenomena matter. They show us the boundary, but they also show us where the cracks might be. Tunneling shows us that quantum mechanics does not treat space as a strict barrier. Phase velocity shows us that speed itself is not absolute. Tachyons, whether they exist or not, show us how delicately causality is protected. And, through them, the universe seems to whisper that faster-than-light motion is not impossible. It is simply structured. It is regulated. It is woven into the laws in ways we do not yet understand. So, as we stand now at the end of these 10 strange chapters, with relativity behind us, and entanglement beneath us, and cosmic expansion all around us, we begin to sense that the true frontier is not the speed of light. The true frontier is the nature of space and time. The limit we keep encountering is not the universe's resistance to speed. It is our incomplete understanding of reality. Warp drives, wormholes, inflation, quantum emergence, all of them point toward a physics not yet written. A physics where geometry and information merge, where spacetime may not be fundamental, and where the speed of light might be a property of a deeper, hidden layer. And, as we look ahead, there is one last question we must face, one that rises naturally from everything we have explored. If faster-than-light travel requires a bridge between quantum mechanics and gravity, between entanglement and curvature, between information and geometry, then perhaps the next step is not a spacecraft, but a new theory. Well, you see, the future of faster-than-light dreams may depend on whether we can unify the quantum world with the gravitational world, whether we can write the equation that binds spacetime to entanglement, whether we can uncover the architecture beneath the universe we see. And that is where our journey must turn next. Toward the future, toward the dream, toward the quiet possibility that the cosmos is far larger, far stranger, and far more open than we ever dared to imagine. And, when we finally step back from all of it, from the warp bubbles that bend spacetime, from the wormholes that tunnel through it, from the trembling quantum fields that weave it, and from the accelerating expansion that stretches it, there's a quiet moment where the universe feels impossibly vast again. Well, you see, after wandering through every strange corner nature allows, we discover something almost poetic. Faster than light is not a single doorway, but a constellation of possibilities. Some are illusions, some are mathematical curiosities, some are real phenomena that simply refuse to be harnessed. And that is what makes the question so enduring. The truth is that the universe is not hostile to the idea of exceeding light speed. It simply protects what must be protected: causality, coherence, the unfolding of time. Warp drives are not forbidden. Wormholes are not forbidden. Inflation happened. Galaxies recede faster than light even now. And quantum entanglement whispers connections that ignore distance entirely. So, the cosmos keeps showing us cracks in the wall, gentle reminders that the speed of light is not a prison, but a feature of the layer we currently inhabit. The cause of difficulty is not the laws of physics. It is our understanding of them. Negative energy flickers through the vacuum, but we cannot gather it. Wormholes open beautifully in equations, but collapse instantly in reality. Quantum tunneling leaps boundaries, but carries no message. Phase velocities outrun photons, but carry no meaning. And, these clues remind us that nature's rules are subtle, not absolute. Barriers, not walls. Well, you see, if faster than light travel ever becomes real, not symbolic, not mathematical, but physical, it will come from a deeper theory. A theory that unifies gravity with quantum mechanics. A theory that explains why spacetime emerges, why light has its speed, why causality holds, and why the universe allows certain kinds of faster-than-light behavior while forbidding others. And that unifying theory may show us that the speed of light is not an ultimate limit, but a property of the geometry we currently occupy. Perhaps one day, in some distant century, when humanity understands the architecture beneath reality, we will discover tools that shape space-time the way ancient sailors shaped sails. Perhaps we will learn to bend geometry, not break it, to ride expansion, not outrun it, to weave connections the way the universe already weaves them in its quantum foundations. And, well, when that day comes, the question will not be how fast we can travel, but how deeply we understand the universe we move through. Because maybe every boundary we see now is just the first doorway, and beyond it lies a cosmos far wider, far stranger, and far more welcoming than we ever imagined. And that is the quiet promise hidden beneath the speed of light.